Okay, so the whole goal of potentiometric measurements is to use a voltage measurement to relate to an E-cell measurement, which ultimately relates to the concentration of some species through the Nernst equation. And so that's the sort of view from 10,000 feet when we're thinking about potentiometry. When we're thinking about designing a cell to measure a substance, cells often look like this. This is a generic representation. I'll show you what a true potentiometric sensor might look like. But this is sort of the really simple representation of what a cell might look like. And it's really just two half reactions where we know one half reaction to a T, meaning it's well defined. We know all the inputs, we know all the concentrations. So that part of the Nernst equation is all known and described. And then we know part of the other half of the cell, but we don't know all of it. And so really it's just setting up a Nernst equation where one of the variables is undefined where everything else is defined. That's it. We measure a voltage as an E cell, and then we use that E cell to compute what the concentration X is. So in this case we have two cells, and I'm going to use this to illustrate potentiometry, but I'm also going to use it to illustrate this idea of what a reference electrode is. So in this case we've got two cells, one of which is well-defined, one of which is not. The well-defined one is on the left, where we have a certain amount of concentrations of everything that's well-defined. On the left we have this silver chloride that is coated, that's the sort of blue color, on the surface of a silver metal electrode. Then we have a solid amount of potassium chloride that is in the solution, which means that the chloride concentration and the potassium concentration, for that matter, are completely saturated in the solution. That's why you have solid KCl just sitting on the bottom, just to keep the equilibrium solubility of potassium chloride fixed. So those things are fixed in solution by the KSP. That's important. Got the salt bridge, and over here we have some amount of iron 2 and iron 3 plus and a platinum electrode. In this case, the platinum electrode is what we call our indicator electrode. Your book likes to call it indicator electrode. Oh God, indicator electrode. I like to call these a working electrode. That's more common in the electrochemical community. Either one works here. So platinum here is not participating in the redox reaction at all. It's simply serving as an inert metal to complete the circuit. Over here though, silver and silver chloride are part of the redox reaction in the system. We're given this redox reaction. We could have deduced it on our own anyway. In this case, because it's the left-hand cell, and we even see it in our shorthand version here, the one in blue, this is the oxidized half reaction, which means then over here this becomes the reduced half reaction. So we can write these half cells up. So this becomes silver plus, so that's silver 0 plus chloride proceeds to make silver chloride solid plus an electron. So what's happening here, this is the silver reaction, except it's happening in the presence of chloride. That's the only difference. So it's still silver to silver plus. So here to here, this is silver plus in that oxidation state. That's where we lost that electron. That's what's happening in the left cell. And then in the right cell, because if this is an oxidation, then the second step needs to be a reduction. So that would have to be iron 3 plus an electron proceeds to make iron 2 plus. So we can look up the E naughts for both of these, which just comes straight from the table. So for the silver chloride reaction we have 0.222 volts, and for the iron 3 to iron 2 we have 0.771 volts. I didn't fudge those in any way yet. Those come straight off the table as written as reductions. So of course this first reaction is not written as reduction, so we need to flip that one around. So we can add these things up, and what we get is silver 0 plus iron 3 plus chloride proceeds to make silver chloride solid plus iron 2 plus. We have an electron transferred in each. So we need to add these two things up. That gives us positive 0.49 volts. That's our E naught cell. That's a standard reduction potential of the cell, or the difference between the standard reduction potentials in the cell at standard temperature and pressure, and assuming 1 molar of everything. So from here we can just draft up a full cell Ernst equation. So that becomes E cell equal to E naught cell minus 0.05916 over n being the number of electrons transferred in the system, just being 1 here, log base 10, and this becomes the product of the reactants. So we've got iron 2 plus here, but remember this is a solid silver chloride, and so that does not factor in to the overall cell potential, which is really nice. I'll tell you why that is for a second, in a second. That's divided then by iron 3 plus, and then chloride ion concentration. So we know the E naught cell because we can compute it. That's just a theoretical value. We know N. We don't know iron 2 plus yet. We don't know iron 3 plus. Do we know chloride? The answer is yes, because chloride is fixed by the KSP of KCl, because it's saturated solution with excess salt. So the solubility product would be KCl proceeds to make K plus plus chloride, which means the KSP is equal to K plus plus chloride equivalent, which would be XX here, which means that, let's move this down a little bit, which means the KSP here is equal to x squared, which means x, where that's the concentration of chloride, would be equal to root KSP. So I say all of that to say that this is a constant. So we don't need to consider that because it's fixed, it's not changing. No matter what we do to this system, if we allow this reaction to proceed in this direction or we force it to proceed in the opposite direction, it doesn't matter. The chloride concentration is fixed by design. And that's because this is a carefully designed potentiometric cell. Look at what our Ernst equation is. Our half reaction contained a solid and a species, the only aqueous species that would show up in the Ernst equation is fixed in concentration. That's clever, right? Because these two are solids, they don't affect the activities in the E cell, and because the chloride is fixed by KSP, it also doesn't affect it. It's fixed. We could just as easily pull this value out and not even consider it. So what does this actually mean? Well, it means that the cell potential is only then a function of the ratio of those two species. And just like our Henderson-Hasselbalch equation, where we had a log ratio like this, every factor of 10 difference or change in the ratio between these two species, that equates to a 0.05916 volt change per electron, if this is 1 electron, which if this is E cell and we're subtracting this, this is volts. This is essentially millivolts if you want to think about it. So what that really means is every factor of 10 change in the ratio between iron 2 and iron 3 in the cell, we get a 59 millivolt change in our E cell, because this is a constant. And this is a constant, and so the only thing that changes is that ratio, just like the Henderson-Hasselbalch equation. This is how a metal ion sensor would work if we built it in a really, really simple potentiometric way. It's simply based on this. So I also want to introduce to you then this clever design in the half cell that doesn't change. We have a name for that. We call those reference electrodes. So this whole box here, you might have been, this is the sort of dashed blue line here, that represents the half cell that we call a reference electrode. And so what that means is often when you're doing a potentiometric measurement, we just construct that as a whole cell by itself, freestanding. It's really a half cell. but it's got a silver wire in it, it's coated with silver chloride, and it's saturated with KCl and water, and then it has a salt bridge attached to it. And we take that whole thing and we build it into its own freestanding electrode. Why? Because then we can just take that silver and measure it against another electrode in a beaker, and the only thing that's going to change the voltage of that cell is what's in the system. Even better, if you don't have two unknowns, if you know one of those, then the only thing that's changing the cell potential is the unknown, which we could then back out of the Ernst equation, which is how metal ion sensors work. So let me show you what a real reference electrode, so you could build it this way if you want. Totally, it would work without a doubt, but let me show you what a modern commercial reference electrode made out of silver chloride would look like, just so you have a reference. So these are just pictures I grabbed really quickly off the internet. These are silver chloride electrodes that you can buy. If you work in my lab, you'll see ones that look a lot like this. They're not exactly these ones, but they're similar. These things are about $25 to buy. They cost you about 50 cents to build. So I also have a lot of these in my lab that you build. If we were doing this class in person, then you would have built one of these to do a potentiometric titration, but unfortunately that was not something we could fit into a kit safely because it uses some fairly toxic reagents. So you're not going to see this in real life. So what this means is this dashed blue line, what we essentially do is take a tube of glass, looks like this. This would be the outer diameter of this, and then we pull it using glass blowing, so it pulls to a little taper like that. And then what we do is, first thing, I'm going to do this in green. We take this little porous piece of glass, which I'm making green here, and that porous piece of glass is our surrogate or our proxy for the salt bridge. Because what it does is it allows diffusion through there of ions, but it limits water, so water doesn't flow. But it allows us to complete this circuit. Instead of having this big, cumbersome, bulky salt bridge tube, we've shrunken that down to this thing, which is this tiny little thing. I don't know what the equivalent size of this thing is, but roughly, I don't know, 5 by 5 millimeters. Tiny piece of porous glass. They call this stuff Vicor. It's got its own really interesting story that relates to World War II that you can ask me about if you're interested. They don't make this stuff anymore, so all the electrochemists in the world bought it up, I being one of them. So I've got a whole package of Vicor for this very reason. So we've got a bunch of them to make ourselves. So then what you do is on the inside of this glass tube, you put a long, thin wire of silver. So this is just silver metal. So thin silver metal, just buy this on Amazon or anywhere. It's got to be clean silver or pure silver, obviously. It can't be a silver alloy. So you take that stuff and you coat it with a really thin layer of silver chloride. And how do you do that? Well, it takes about 2 minutes. You take your, I'll just show you over here. You take your original silver wire and you plop it into a beaker, and then in that beaker you have 1 molar, anywhere from 0.1 to 1 molar HCl. So you essentially have hydrogen and chloride ions floating around, and you then connect this to a power supply, and you just have some counter electrode over here, doesn't matter what it is, some chunk of metal, and you apply a positive voltage to this side and a negative voltage to this side. What does that do? It drives exactly this first half reaction. Silver plus chloride makes silver chloride plus an electron. So that coats the outer surface. If you run this for about 30 seconds, you'll see a dark sort of sepia tone. That's the silver chloride that forms on the surface. And then you pull that electrode out and you put it into this glass tube, coated, and then you fill this thing up and you cap it. So you cap it like this with a little rubber cap, just like this here. And you fill this thing up with saturated KCl, which is what this stuff is here. How do you do that? Well, you just make a saturated solution by dissolving as much KCl as you possibly can, even heating it up if you need to. Once you get it saturated, you add a couple extra grains in for good measure. So you add a couple grains in here is what I like to do, and then I fill this up all the way up. And you have, in this tiny little this little encapsulated cell, you have this entire half reaction. So now what do you do with it? Well, let me erase something really quick. So now you just pop it into a beaker with your unknown. It could be iron 2, it could be anything, some other redox active species, and you couple that with that original indicator or working electrode. I'm just going to call it working because that's what I like to call it. Just like you had in your original cell, but instead you've taken that whole other beaker, that whole salt bridge, all that extra junk, you jammed it into this tiny reference electrode because you made it or you bought it. And now when you connect your multimeter to this thing, it's literally the same thing, except that entire thing is now encapsulated in this tiny electrode. Ion transport goes through that little Vicor frit, so we've got a complete electric circuit, and the Ernst equation is fixed and defined so that the only thing that changes it are the ion concentrations. That's how a potentiometric cell would work. I should also mention there's plenty of other reference electrode half reactions out there. I like to use silver chloride because it's really clever, because it has no potential change. Even if you run this electrode in either direction and destroy some of the silver, that chloride is just going to eat it up really quickly and create more silver chloride. And if you run it in reverse, what that's going to do is create more chloride in the solution. But what that'll do, because it's saturated, is it'll just precipitate out as potassium chloride. So you can run this reaction as much as you want, and the potential is always going to be 0.222 volts. It's a beautiful reaction for that reason. There's other ones out there that are like this, one of the most common being Mercurous Chloride, which is Hg2Cl2, and it's an analogous reaction from pure mercury. But as you imagine, that requires a cell like this, and then inside of there is a big plug of liquid mercury to complete the half cell. If you break that, then you've got mercury laying around, as opposed to if you break your other one, you have silver, which is completely inert. So this old school Mercurous Chloride electrode, you'll see this if you do more electrochemistry. They call this the calomel electrode, or the standard calomel electrode, and it goes by SCE for short. It's almost as popular as the silver chloride electrode, but as we move into the modern age and electrochemists get old, this thing is no longer as popular. I don't have them in my lab, but I definitely used them when I was in graduate school. There's other things out there. Those are the two most common, but as you can imagine, anytime you can create a system where you can run the redox reaction, the half reaction, and it doesn't change its fixed potential, then you have a good candidate. If you then on top of that make it so that it's cheap and easy to make and non-toxic, then you've got a real winner, and that's where silver chloride is. So I probably have 20 of these things or more laying around my lab just because they're so cheap and easy to make. So remember then, any voltage that ever gets measured, ever, in an electrochemical cell is always going to be with respect to some standard reference electrode. That's always going to be true. There's no such thing as just measuring 0.45 volts in a cell, ever. You can't do that. It always has to be with respect to the other half of the circuit. And either that other half of the circuit is a floating electrode like a platinum wire that is changing, which is bad practice because it's changing, so it's a non-stable measurement, or it's versus a standard electrode, some reference cell that either you purchased like this in a prefab form, or you constructed like this in the non-prefab form. You just made it in a beaker. Either way, the way that cell voltages will always be reported then is going to be some voltage versus SHE versus silver chloride versus SCE, etc. That always has to be true. So anytime you're labeling an axis with voltage, be sure you're telling exactly what potential you're referenced to. That's super important. Otherwise, there's no bearing in electrochemical space. That it means nothing to just report a voltage without telling me what you're measuring that voltage against. And so I like to convert these. So often I read papers and somebody might report it in SHE, but I'm a silver chloride guy, so I want to be able to convert between the two. I think it's helpful to think about these as a number line where you have SHE, that's standard hydrogen electrode, that's 0 volts by definition. Silver chloride with respect to SHE is 0.22 and SEE is 241, and so you can interconvert between these simply by thinking about it as a number line. That helps keep your signs in good order.